我们今天的 speaker 是陈彦佐，Yanjoe Tan. So Yanjoe started his early life in Malaysia and as well as in Singapore. Then he went to college at Lafayette College in Pennsylvania. It's about 2 hours of drive to New York City. Probably that's one of the reasons why he chose to start his PhD in the New York City at the Columbia University, the Lamont Observatory. Later on, Yanjoe did a 1-year postdoc at Stanford University. And just yesterday, right? Yeah, yesterday, Yanjoe started his new position in his office at the Chinese University of Hong Kong as an assistant professor. So Yanjoe has a very broad international experience, not only in Malaysia, Singapore, later on the East Coast of the United States, West Coast of the United States. He also spent time doing research at Los Alamos National Laboratory in the central part of the United States. And he also has been visiting research projects in France, Europe, as well as doing the study abroad projects when he was undergraduate in double major. One of the other major other than geology was in sociology and anthropology. I think that's probably the reason that brought him to Africa, in Kenya and Tanzania for a couple of months for international training program. So being a seismologist and also pursuing various questions in volcanology, Yanjoe has been, of course, working with the scientists and study areas around the world. So with that, I will give the rest of the time for Yanjoe to give us a presentation, and later on we'll have more questions for interaction. So Yanjoe.
Okay, thank you, Zhangzhou, for the introduction. And good morning, everyone. Maybe good evening to some of you. So today I'll be presenting results that's coming out of what I think is a very interesting and unique seafloor observatory that has been set up on Axial Seamount. But before I start, I would like to acknowledge my collaborators. So the results that I'll be presenting today are have primarily been done through collaborating with Maya, Felix, and Chris Schultz at Columbia University, as well as William Wilcock from the University of Washington and Fabian Abino from University of Bristol. And so, as an introduction, Axial Seamount is a submarine volcano. It's an active volcano that is located offshore the United States. So this black box here is the figure to the right here is zoomed into this black box here. And so on the right, you can see this is the west coast of the United States, and this is where Axial Seamount is. It's formed at the intersection of between the hotspot as well as the Juan de Fuca Ridge. And it is one of the more active submarine volcanoes that we know of. And over the past 2 decades, there have been multiple expeditions that have gone to Axial Seamount to study the different geological and magmatic processes at this site. And so because of that, it was selected as a site as part of the Ocean Observatory Initiative to set up a permanent network to monitor this active volcano. And so since late 2014, we have a network that's been set up here. So this is a zoom in on Axial Seamount, and you can see the caldera rim. And on the caldera summit, we now have seismometers, tilt meters, bottom pressure sensors that record vertical deformation, HD cameras, a range of instruments that have been set up on this permanent network. And we have fiber optic cables that connect these instruments to onshore. And so because of that, we have real-time data that's coming in from a range of instruments, and it's publicly available. So anyone can download it from the data portal. And so based on this data, luckily for us, about 4 months after the network was set up, the volcano actually erupted. And we inferred that from analyzing this real-time data that was coming in from the seismometers and bottom pressure recorders. And because of that, we actually subsequently sent a cruise to go out to the site because we knew that an eruption had recently occurred. And so we sent our crews out there to try to map the lava flow boundaries and also to take to collect additional data. And so this is a video collected by submarine where they found where the fresh lava flow is. And you can see that there's all these bacteria flock. So these are bacteria mats that were formed shortly after an eruption. And so these are very fleeting biological processes that's deeply coupled with magmatic processes at submarine volcanoes, and it would not have been possible to collect such data because if we only showed up 6 months after the eruption, these processes would have ended. And so this shows the strength of having real-time data coming from a submarine network. And so since then, so it's been 5 years since we have data streaming continuously from this network. And so since then, we have actually set up a real-time analysis of the seismic data. So based on the seismic data coming in from 7 seismometers, so we have 7 seismometers around the caldera, we now build a near real-time high-precision earthquake catalog, where we have an earthquake located within a minute from its occurrence. And so this catalog is also publicly available online, and so anyone can download the data. And the idea is that we're trying to build this open access data portal such that different communities can use this catalog to learn about different processes. So in this video, you can see that there's a sudden burst of events around April 2015. That was when the eruption happened. And so because of this, we have been able to infer and learn a lot about the magmatic and volcanic processes that's occurring at axial volcano, and to understand the different geological processes that control eruption dynamics at submarine volcanoes. But today, I'm going to talk on a slightly different topic because we have recorded a lot of earthquakes, and this actually provides us a very good opportunity to understand and probe different earthquake processes. And so today I'm going to talk about how we can use data coming out from this network to understand how seismicity rate, as well as the earthquake size frequency distribution, is affected by stress changes. And so why axial seamount? So why background seismicity rate in a small region? And so from the map before, you can see that the volcano is only about 4 by 4 kilometers. But then within this small region, we located about 60,000 earthquakes within about 3 months before the eruption. So that gives us a lot of events to work with and do statistical analysis that might not be possible in other regions. And secondly, we have relatively large periodic tidal stress perturbations at this site. And so this tidal stress changes due to the gravitational pull of the sun and the moon creates this periodic stress changes. So we are kind of in this unique environment where we have a natural lab that is similar to a rock mechanics lab, right? Where we have a piece of rock, a small piece of rock, that's having periodic stress changes, kind of like a moving piston. And then we have a lot of earthquakes that's coming out from this piece of crust, and then we can probe how the earthquake statistical properties vary systematically with tidal stress. And so, going back to a more basic, the big question that we have to first answer is, can tides trigger earthquakes, right? So we know that tidal stress changes is very small. It's on the order of kilopascals. And so these are very, very small stress changes compared to what we know of a typical earthquake stress drop, which is on the order of megapascal. But at the same time, we know that tidal stressing rate can be much larger than tectonic stressing. So in this plot here, this is in a paper by Van der Elst et al., where they kind of model the background tectonic loading induced background stress. And you can see that there's a slow build-up of tectonic stress, right? And even though tidal stress changes is small, you can see that it moves up and down, and the stressing rate is quite high compared to the background stress. So if an earthquake occurs when a peak stress threshold is reached, one can imagine that when a fault is close to failure, the tidal stress can provide the last kick that kind of triggers an earthquake. And so this idea has been around for a long time, and people have been looking for evidence of tidal triggering of earthquakes over the past century. And so, do tides trigger earthquakes? So in this review paper by Amter in 1997, he looked through 100 studies within the past 100 years, and he found that there's papers that argue that there is evidence of tidal triggering of earthquakes, as well as there are papers that say that there are no evidence of tidal triggering of earthquakes. And they occurred equally often. And this continues to this day, where there are still papers coming out with some saying there is tidal triggering of earthquakes, and others saying there isn't. But even though a lot of these studies look at global earthquake catalogs, and what they often do is they look at the tidal stress time series, right? So this is the periodic tidal stress changes, and then based on the earthquake origin time, they assign an earthquake phase to it. So if the earthquake occurs at the low of tidal stress, you'll get a phase of either minus 180 or 180. And if it occurs around the peak of the tidal stress, you'll have a phase of 0. And then you can subsequently plot the histogram of the tidal phase. And if earthquake is completely uncorrelated with tidal stress, you would imagine that you would get a uniform distribution, right? Whereas if earthquakes occur preferentially during certain tidal phases, you will see a peak of seismicity rate during a certain time period. So in this paper by Cochrane et al. That was published in Science back in 2004, this is what they did. They looked at subduction zone earthquakes that are at shallower than 40 kilometers depth. So the rationale for looking at this subset of events is because since they are shallow, they have lower confining pressure. And in subduction zone, because we are in an oceanic environment, the tidal stress changes due to ocean loading is larger. So they then did the analysis that I've described previously, and they plotted the earthquake tidal phase distribution. And you can see that this is the distribution that you get. And you can see that the earthquake rate kind of peaks at the tidal phase of 0. So from this, they concluded that there is evidence of tidal triggering of earthquakes based on analyzing a global catalog of subduction zone events. But actually, this figure is only based on 250 earthquakes that occurred during the times of the largest tidal stresses, whereas the signal is much weaker when they look at the whole catalog itself. And so personally, I would say that based on a lot of papers that have come out in the past 100 years, when you look at global earthquake catalogs, the signal of earthquake tidal triggering is weak at best. But as it turns out, the signal of tidal triggering of earthquakes have been well documented at mid-ocean ridges. So mid-ocean ridges, this is a global map of mid-ocean ridges with the ridges outlined in red. So this is where the tectonic plates are spreading apart. And at sites where we have had deployments of ocean bottom seismometers and have a good enough earthquake catalog, such as on the Juan de Fuca Ridge, as well as the East Pacific Rise, people have shown very strong evidence of tidal triggering of earthquakes. So in this example here, in this paper by Struve et al. In 2007, they plotted the number of events per hour against tidal stress. And you can see that the number of the earthquake rate increases systematically with tidal stress. And so the question that comes out from studies like this is that, is there something special about mid-ocean ridges that make it especially sensitive to tidal triggering? And if it's so sensitive to tidal triggering, can we use this data coming from this site to better understand and probe the physics of what controls the sensitivity of these sites to small stress perturbation? And what does it tell us about earthquake nucleation processes and how stress controls earthquake nucleation? And so Axial is a good site to do this, I think, because we have a lot of earthquakes in a small region. So as a reminder, this black line here is the caldera rim of this volcano. We have 7 seismometers on this site, and we located 60,000 earthquakes in 3 months. So the earthquakes are mostly on the west and eastern side of the caldera rim. And if you take a cross section with that, so this plot here on the right, you can see that the earthquakes clearly delineate 2 outward dipping faults that goes down to a depth of about 2 kilometers. And they are right above the top of the Magma reservoir. And so, based on focal mechanism analysis, we know that right before the eruption, whereas the volcano inflates, we predominantly have normal faulting earthquakes. And so, when we plot the number of events per hour at Axial, so this is over a 2-week period, and the red line here is the ocean height. So you can see that there's very, very strong evidence where the seismicity rate increases, right? You see this burst of events occurring, correlating very strongly during times of low ocean height. And so the evidence for tidal triggering of earthquakes at axial is very, very strong. And when we make a plot of the histogram of the earthquake tidal phase, you can see that it jumps out very strongly that earthquakes are occurring preferentially during times of low ocean height. But even though the statistical evidence of tidal triggering is very strong, something that baffled us for a while was that when you actually calculate the Coulomb stress changes on these normal faults, a decrease in ocean height should actually inhibit the faulting event. So rate would be so this is a plot of Coulomb stress change on 67 degrees outward dipping normal faulting events. So red would represent them being encouraged during low ocean height, whereas blue is where they're inhibited. So this puzzled us for a long time because so you have decrease in ocean height that decreases the normal stress, so that should encourage earthquake. But because the shear stress is in the opposite direction, when you have the combined effect, which is quantified by the Coulomb stress, this actually should have inhibited normal faulting events. So even though we have strong evidence of tidal triggering, the phase of it is exactly opposite of what we expected. And it took us some time, and eventually the explanation that we came up with boils down to the existence of a magma reservoir directly underneath this fault. And so we know about the existence of a magma chamber based on active source imaging. So people went out there, they set off a bunch of explosions from the ship, and the waves coming out from it gets reflected from different layers. Right? So from that, you can image the different subsurface structure. And so in this paper by Arnold et al. In 2014, they used data from this, and they managed to image the existence of a magma reservoir underneath the exit volcano. So we have a large magma reservoir that's 14 kilometers in length, 3 kilometers wide, and about 1 kilometer thick. And it mostly is about 2 kilometers below the sea floor. And so when we incorporate the effect of this magma reservoir and model the stress changes due to this, what we find is that, so when we model the stress changes due to the inflation of this reservoir, you get on this normal faults, you can see that it encourages the occurrence of earthquakes in the exact region where we see a lot of seismicity, right? But then when we also model the stress changes due to changes of this magma reservoir from a 1 meter decrease in ocean height, we see the same pattern of Coulomb stress change. And this is because when the ocean height decreases, because the bulk modulus of the magma reservoir is different from the surrounding rock, right? It has a lower bulk modulus. What then happens is that the magma reservoir actually inflates relative to the surrounding rock. So this creates a stress pattern that's similar from when the magma reservoir is inflating from increase in melt into this region. And so the net Coulomb stress change of this fault is the combined effect of this magma inflation with the direct tidal loading effects. And the net stress changes, whether it's positive or negative, boils down to what the magma reservoir's bulk modulus is. And so when we model how the Coulomb stress change is on this fault relative to the bulk modulus of the magma reservoir, keeping the bulk modulus of a surrounding rock constant, we can see that there's a regime where during low ocean height, we would be encouraging reverse faulting if the bulk modulus is greater than 7 gigapascal. Whereas if it's less than that, we will start having normal faulting events. So simply from the observation that we have increased normal faulting earthquakes during low ocean height, we know that the bulk modulus of the magma reservoir is likely to be less than 7 gigapascal. And so we are in this rate regime. So from this, we can then convert the tidal stress to Coulomb stress change on the fault. And we can then quantify how earthquake stress changes, how seismicity rate varies with stress change. And so this is what we get. So the y-axis here is the normalized earthquake rate. So it's normalized against when Coulomb stress change is 0, right? So when Coulomb stress change is 0, this factor is 1, right? So the top of this is the earthquake rate. And we can see that the seismicity rate increases systematically with increase in Coulomb stress change. And the red line here is a fit to the rate and state friction model. So this is a very popular theoretical model to understand, to explain how stress changes would relate to seismicity rate. So the top here is the Coulomb stress change. And the bottom here is the rate and state friction parameter that I'll talk about later. And sigma here is the effective normal stress. And so this is the fit to our data. And you can see that our observation fits the theoretical model really well. And just from this, we can conclude that there is no triggering threshold. And so from previous studies, some people have argued that earthquake triggering can only occur when there's stress changes above a certain amount. So that has partly been used to explain why we don't see triggering when the stress changes is too small. But from this observation, you can see that the house earthquake rate varies with stress. It goes all the way from negative to positive, and so there's no triggering threshold. And what people have often talked about, which is the effect of stress shadowing, is actually a simple continuous function of stress reduction. And so aside from that, what we can then probe is that we can try to understand this A sigma effect. So the A is the rate and state friction parameter. In the past, it has only been quantified using lab experiments, whereas it's very hard to know what the A value for natural form is, because it's often also hard to estimate sigma n. So, but in this case, we know that our average earthquake depth is 1.2, and if we assume hydrostatic pore pressure and a friction coefficient of 0.8, we would get an effective normal stress of 7.2 megapascal. And so if we plug it into this equation, we get an A friction parameter that's an order of magnitude smaller than lab measurements that have been collected over the past few decades. And we are so in other studies, the big uncertainty here is the effective pore pressure, right? So it's very hard for them to estimate the effective normal stress. But in our case, and so what often happens is that people plug in the lab values and then they infer the effective normal stress. And what often happens is that they need near lithostatic pore pressure to fit the observations. But in this case, because we are in a young oceanic crust, we have no sediment covers, and all these earthquakes are occurring in the top 2 kilometers of the oceanic crust, and we have vigorous hydrothermal system in the surrounding region, we are very confident that we don't have lithostatic pore pressure, and that it is only hydrostatic pore pressure. So this gives us a unique environment for us to constrain what sigma m is. And I think this is one of the first measurements of the friction parameter of a natural form. And we find that it's significantly smaller than that measurements. And so this explanation where the existence of a magma reservoir can significantly affect the stress field in the surrounding has potential applications to other observations. So for instance, in Iceland, the Katla volcano, they have found that seismicity rate correlates with seasonal unloading and loading of ice caps. And so a similar model can explain why they observe this correlation and the type of earthquakes they occur during the seasonal unloading and ice caps. And recently, in a paper by Maya, she has also suggested that mid-ocean ridge eruptions might actually occur preferentially during low ocean height. And so this could also, like our model where magma reservoir inflates relative to the surrounding rock due to the unloading of the ocean height, might be a mechanism to explain this observation. And so in conclusion, what we found from this study is that the existence of a magma chamber changes the stress distribution due to the tides, tidal loading, and the long observed sensitivity of mid-ocean ridge earthquakes to tidal stress changes is partially due to the shallow depths. But another reason is that we have quantified the real-estate friction parameter A, which kind of explain the viscosity, which kind of parameterizes the viscosity of the fault, hence the sensitivity to tidal stress changes. And we find that for natural faults, they're significantly smaller than lab measurements. And so other studies shouldn't just blatantly use lab measurements and plug it in to infer the pore pressure at the natural faults. And finally, we don't observe any triggering threshold. And the long talked about stress shadow effect of earthquake due to stress changes is simply a continuous function of stress reduction. And so this concludes the first part of my talk, and I think maybe this is a good time to pause for a little bit and see if there are any questions that people might have.
Okay, great. I think we will have questions from the audience because I think at least I see one author that you cited in your talk is in the audience. So go ahead. So if you have any questions, feel free to ask or type the questions. 大家也可以打，如果说问题的话，你可以用中文问也没有关系，或者打字打中文也没有关系，我们会帮你翻译。OK， 大家有问题的话，现在可以开始提问。战燕，请给 OK。Hello.
Hi.
Can you hear me? So I'm not sure. Like,
yes.
Okay, Wang Wei. Yeah. Wang Wei, go ahead. 战燕第二个回答了。OK， Wang Wei, go ahead.
Okay. So 我有一些。就我用中文的方便其他人可以更容易听清楚。So yeah， 我就是那个no evidence 的那个 author。
Okay.
Yeah. So yeah， 我的问题是这样子的。因为你们在 pre eruption 和 after eruption 时候，之前和之后它的那个 focal mechanism 会有明显的改变，然后从那个 recent state 里面可以明显看到它的抑制和那个和触发的关系实际上是有一个明显的不同的。你们比较过，就是相当于震前和震后，他们是不是会出现那种触发的，就相当于触发的类型会有一些不一样？这第一个问题。第二个问题就是说，你们触发的时候是不是会有一些 time delay？ 因为尤其是 remote triggering， 大家一般会 argue 的一个问题就是说 ，somehow 就是说你有一个stress seismic wave，
是的
right here and just because of a latent state or some different kind of model， 所以说它就有一些 delay triggering。所以说你们会有一些 delay triggering 吗？
So I'll translate the question just because there are I know some audience who doesn't speak Chinese, and so the first it's okay. So the first question is the focal mechanisms, right? So we know before the eruption we have normal faulting events, right? And then during the eruption we have thrust faulting events, and then after the eruption we have normal faulting events again. And so in this paper we only look at the period before the eruption. And so because we wanted to be confident that they are all normal faulting events and we are making a good inference, right? But I have also looked at after the eruption and during the eruption. And during the eruption, there's a flip in that we see more earthquakes during high tide instead of low tide.
Yep.
But it's a bit tricky because during the eruption, there are also other magmatic processes that controls the occurrence of earthquakes, right?
Right, possible, yeah.
But at the very least, it is consistent with our interpretation.
Okay.
The second question that the author asks is whether we see time delay, because people have studied dynamic triggering, and dynamic triggering is very strong and a lot of volcanic and hydrothermal sites. And one of the perplexing thing is that people see a delay in the triggering, right?
Yep.
But we don't see that for tidal triggering at the very least. So you can see this phase distribution. The peak is right at 0.
Right.
And so we do not see any delay in triggering. Yeah, and we have looked at it too. We have tried to see whether there's any sign. So at least from tidal triggering, we do not see any delay. And right now it is we are one of my students is trying to look at dynamic triggering and axial to try to see whether we see dynamic triggering, and secondly whether there is any time delay. And the strength of axial is also that we have hydrothermal vent fluids measurements continuously as well. So like explanation, some of the explanations that people have give for delay in dynamic triggering is that there's poroelastic effects, right? There's pore pressure wave perturbations. And so we will be able to verify that by looking at hydrothermal venting measurements as well. So it is pretty exciting. That's something we're trying to look at.
Okay, yeah, thank you. Yeah, I just have one update information for our paper, because for that Japan study, so we find no tidal triggering, and also we still look at the Southern California, use the original Southern California catalog. So, but recently we update our results. We find like the solid Earth tidal triggering in some geothermal field in Southern California, and also we have because you look at the low tidal triggering, the tidal triggering happens as a low tide, but we look at high tide and no time delay. So I think it's.
Hello, I think you got cut off. Am I cut off or is he cut off?
I think
way is
just
off.
muted.
Ah, okay.
You are okay. You're fine.
Okay.
王威现在还能继续听见吗？我猜他应该掉线了。Okay， 那请詹岩 ，yeah, you can continue. 詹岩 could ask a question. If we comes back, we could let him to showing his update. Okay, Zhang Yan, please go ahead.
Hi, Yanjoe. Great talk. Very interesting topic. I have two questions. One is, so you mentioned the bulk modulus of the magma reservoir, and in different domain, it would trigger different type of the earthquake. So my question is, what's that bulk modulus compared to the host rock elastic property?
Right. So the host rock, we put it at 55 gigapascal.
55. Okay. So if you change that, like Young's modulus, will that domain also change? So
yeah. So So our result is not sensitive. So our result is not that sensitive to the exact value of the bulk modulus, because we know that normal faulting events are being triggered. So we are in a rate regime, right? Okay. But when we fit this, right, it doesn't matter what this value is, right? Because it would just be, it would just map into the A sigma value, right? So how well this fit is works as long as we are in this rate regime. But in this paper, to subsequently infer the A and the sigma n, we pick a bulk modulus value, which is at about 1 gigapascal. And honestly, this value is a bit small for the typical estimated bulk modulus of mid-ocean ridge basalt. But if we increase the bulk modulus, it would actually make the sigma, the friction parameter, even smaller. So the conclusion that the friction parameter is smaller than lab measurements stands if we use quote unquote more reasonable bulk modulus value. And we think the bulk modulus that we choose can be explained if we have, say, exsolution of CO2 and H2O, right? Essentially volatiles in the magma reservoir. So originally we were quite excited. We were thinking that maybe we can use tidal triggering to constrain the bulk modulus of the magma chamber, right? But then subsequently we realized that the friction parameter is not well constrained enough for us to do that. So we had to do the reverse, where we assume a bulk modulus and go from there. But the main conclusion from our talk, which is that this existence of a compressible magma chamber stands because we are observing normal faulting events. So to a certain extent, we need to be in this rate regime. And the explanation that the friction parameter is significantly smaller than lab measurements also stands because we don't have much more space. Like even when we use a bulk modulus close to 0, the A value is still like 5 times smaller than lab measurements. Does that explain your question?
Sure. So do you assume the overpressure in the magma reservoir is keep constant during the tidal change?
Yes. So the tidal change is over 12 hours, right? And we are stacking over, 3 months. So
yeah, to me, since you mentioned there's no time delay in the phase, or maybe there is a 1 pi delay, but but if we assume there's no delay, it's more likely everything happened is outside magma reservoir. Since inside magma reservoir, due to the viscosity, they may have some delay to change the pressure. But it seems if there's no delay, that may mean the tidal just changed the stress of the host rock and trigger earthquake. So my
So like when we say there's no delay, right? There could be a delay of say 5 degrees or 10 degrees, right? It's just, but it wouldn't stand out. It doesn't stand out as strongly from our data.
And you also related to your the rate state fraction model. So you mentioned there's no obvious threshold. So for even negative Coulomb stress change, they can also have a stress rate change. So my question is, in your observation for the tidal, the wave of the tidal, we also see there's some small peak and valley. So for those small signal, do you also see the increasing or decreasing of the earthquake rate?
You mean
the observation?
Here is it?
Yes.
Yeah. So like you see, right? There is when there's a smaller trough, right? You still see a little bit of peak, right? In seismicity.
Perfect.
It's just noise peak.
Yeah. Thank you.
Yeah. Thanks for the questions. Any other questions?
Hi, Professor Tan.
Hi.
Very nice talk. Thank you. And
王明浩，你的声音再大一点。
what about this sound?
What about the sun?
Can you explain more on what is the difference between normal faulting and reverse faulting when it comes to the impact of tidal stress?
Okay. So normal faulting is when the fault slips. So we have an outward dipping fault. Can everyone see? Actually, you all don't see my face, right?
Yeah, we can see that.
Okay. So if you okay. So the normal fault is when the top fault block drops downwards, right?
Yeah.
Whereas reverse fault is when the fault block goes upward. The normal fault, the top block goes upwards. Okay. So you can think of it simply as this. Okay. So when the tide, say during low tide, right, you cannot encourage both normal fault and reverse fault, right? Because the shear stress is in a complete opposite direction, right? And so during low tides, if you calculate the shear stress, so stress on this fault plane, parallel to the slip direction of the fault, during low tide, the shear stress increase is actually in this direction, right? So if the fault is trying to move in this opposite direction, then the stress that's opposite to its slip direction would discourage it from happening, right? Whereas if for normal faulting events, the fault is trying to drop downwards, and you have extra shear stress pushing it downwards as well. So then it makes it easier and it encourages it to occur.
Oh, I got it. Thank you.
Does that make sense? Okay.
Yeah.
Okay, when you ask question, please first show your identity. For example, the very first question was asked by Wei Wang, who is currently postdoc at University of Southern California. And second question was raised by Yanjoe Tan, currently a postdoc at the Carnegie Institution of Science. The third question was asked by Pinghao Wang from Beijing University, who is currently actually an undergraduate student. So I think with that, let's move forward, Yanjoe, with your time.
Okay. So we have about, let's see, we have about 15 minutes. Should I just jump straight to the end? Okay. I think that's time. Okay. So the second part of my talk, I'll be talking about earthquake size frequency distribution. So I made this part shorter. And so in the earthquake literature, we often talk about it as the B value. And so a very well observed and well quantified statistical property of earthquake is that earthquakes follow the Gutenberg-Richter relationship. So what this relationship is that when you plot the number of earthquakes for each magnitude bin, and you plot it against magnitude, we have a power law distribution, where the slope of this line is called the B value. And people have found that the B value is typically about 1 for tectonic earthquakes. So this plot here is from the global earthquake catalog, from the CMT catalog. And you can see that there's a straight line from magnitude 5 and above. And it disappears below because of the magnitude of completeness. So we are not really detecting all the events below magnitude 5. So it follows a very nice straight line of slope of 1. And so in the 60s, Chris Schultz started doing these experiments in the lab where he squeezes rocks and then they generate a bunch of lab quakes. And he then measures the B value, so the size frequency distribution of this lab earthquakes. And what he found is that the B value varies systematically with the stress difference, so the stress that he loads on this rock. So this was very exciting result because it's very hard because there's no in situ stress measurements on faults. They are at 10, 20, 30 kilometers depth. But if B value does reflect the stress state of the fault, then we can actually use this to infer the stress state of natural faults, and that could maybe help us better understand whether a fault is close to failure. So people got really excited about this result, and they started looking for B value variations for natural earthquakes and to see if they can figure out if natural earthquakes are similar to lab earthquakes in that the B value reflects stress changes. So in this paper that was published in Nature in 2005, they looked at B value variation with earthquake focal mechanisms. And what they found is that normal faulting earthquakes have largest B values, whereas thrust faulting events have smallest B value. And in another paper by Spada et al., published in 2013, they found that earthquake B value varies systematically with depth, where the B value is high for shallow earthquakes, and it increases and it decreases to about 0.8, down to at the depth of about 15 kilometers. And this both this observation, the fact that B value varies with focal mechanisms and B value varying with depth, can be explained by this idea of varying differential stress. So based on the Anderson's faulting theory, the minimum differential stress that's required to initiate sliding varies with depth as well as with focal mechanisms. So normal faulting events are able to start sliding at lower differential stress compared to thrust faulting. And then this also varies systematically with depth. And so Chris Schultz, in a paper that he published in 2015, he tried to convert this variation with focal mechanism as well as variation to depth to differential stress. And when we plotted this B value against the differential stress, converted stress, he found that the data points collapsed very nicely. And from this, he managed to calibrate the measurements. And he found that B value varies by about 0.001 per megapascal. So we are talking about very, very small changes in B value for 1 megapascal increase in stress. But even though this is the interpretation, it is still debatable because there are other factors that have been suggested to being able to affect the earthquake B value. So one of it is the degree of heterogeneity. So in this paper, they suggested that when you have more heterogeneous medium, you can have higher B value. And this was used to explain why B value changes with depth. That this depth dependence of B value does not necessarily reflect changes in differential stress. And in another lab experiment, they also found that the fault roughness might also affect B value, where when you have rougher fault surface, you have higher B value. So what this means is that because there are more smaller asperities, you have more small earthquakes when your fault is rough. And so because we don't have in a typical natural environment, we are not able to control for these other parameters. It is hard for us to definitively say what observed B value variations is due to. And the last disadvantages of using a natural earthquake is that oftentimes people have to use bin sizes of only a few hundred earthquakes and having to aggregate over large regions because they don't have a highly dense seismic region. And so once again, Axial came in as a good region to try to probe this relationship because we have a lot of earthquakes within a very, very small region over a short period of time. And so when you look at tides, we are quite confident that the fault roughness doesn't change over a 12-hour time period. We also know that the heterogeneities also doesn't vary over a 12-hour time period. And so because of that, we try to use tidal stress to probe whether the earthquake B value varies with stress. And so this is a histogram of the earthquake, the number of events for different stress bins. And what we do is we look at how the B value varies for each 2 kilopascal stress bins. And this is what we get. So for each bin, we calculate the B value and we do a bootstrap to estimate its uncertainty. And we find that the B value is relatively constant up to about 5 kilopascal. And then subsequently, it decreases systematically with increasing stress. And when we use the chi value from the talk I talked about previously about the magma effect, we get that the B value varies by about 0.2 kilopascal, 0.2 per kilopascal. So this is orders of magnitude more sensitive than the calibration that Chris Schultz got from analyzing depth and focal mechanism dependence of B value. And so this suggests that the B value the earthquake sensitivity to and its changes of size frequency distribution to stress might be variable between regions. For instance, at axial, because we are shallower, and as well as other effects like pore pressure effects might affect the sensitivity of the earthquakes. And so yeah, essentially we did a bunch of statistical tests to verify the statistical significance of our results because we have a lot of earthquakes, right? We have tens of thousands of events, and when we split the events between quote unquote the lower stress bin and the higher stress bin, you can see very clearly that the slope of the magnitude frequency distribution clearly separates out between the higher and lower tidal stress group. And so our observation has implications for other studies. For instance, many studies have suggested that they see a decrease in B value leading up to big earthquake. So this was before the Tohoku earthquake in this paper that was published in 2012. And they see that over a 10-year period, the B value systematically decreased from 0.7 to 0.5. And if you use the calibration by Chris Schultz, where B value only varies by 0.001 per megapascal, we are talking about differential stress changes on the order of 100 megapascal, which is way higher than the stress drop of an earthquake. And so it's hard to physically understand why we would observe such large changes in B value. But from our observation that the earthquake can be quite sensitive, depending on the region you're in, it might be able to explain this observation. So maybe when a fault is closer to failure, it is more sensitive in terms of the B value variation to smaller tidal stress perturbation. And so, in conclusion, what we find is that earthquake B value might vary, seems to vary systematically with stress. There might be a threshold amplitude, even though that's hard to explain because we don't observe a threshold requirement for changes in seismicity rate. But it might also be that what we are seeing here is a non-linear effect. And so at low tidal stresses, because the changes is small, we kind of see a flattening effect. And we also see that the sensitivity of earthquake B value, the stress changes, might be variable. And so I'm going to end because Zhang said that this workshop that you are in is about machine learning. I'm going to end by briefly discussing how I see machine learning methods can improve our understanding of earthquake processes. And so one of the things that have been really exciting that have come out in the past few years is that machine learning methods have been used to train models that are able to detect earthquakes and pick and associate the phases. And so for those that don't know, so a very basic processing step in locating earthquake is that we have continuous seismic data, right? And then say an earthquake comes in. So we need to pick to first detect that an earthquake has occurred. And then secondly, we need to pick the time of arrival. So we need to pick the time of arrival of the P wave and then the time of arrival of the S wave. And historically, a lot of this has come from manually picked waveform. So for instance, the Northern California seismic network has been picking, there are humans there sitting there every single day, picking through these earthquakes and picking the arrival. So the great advantage of this is that means that we have a lot of manually labeled data. We have millions and millions of seismograms that have been labeled. And so a lot of papers since then have used this labeled data to train neural networks to pick events. And based on what I've tried out so far, they seem to have done a very, very good job. And the key advantage of this, of having a machine learning based method, is that firstly, they don't get tired, right? So humans get tired from picking events. And so when there's a big earthquake and there are a lot of aftershocks, what oftentimes happens is that the smaller events don't get picked because the analysts are overwhelmed. And the other thing is also analysts are slower, whereas this machine learning trained phase pickers are very, very fast. And you can scale that indefinitely as long as you have more computers, right? And they are very, very consistent. So there's unlikely to be, there might be variations between different analysts, right? So if there's a new analyst that comes on board, they might pick differently from previous analysts, whereas consistency is pretty much guaranteed when it comes to computers. And so here's an example of a project that I worked on where we look at this central Italy earthquake sequence from 2016 to 2017. So this was a big earthquake sequence. There were multiple magnitude 6 earthquakes, and it caused a lot of damage in Italy. And hundreds of people died from this event, this sequence of events as well. And so on the left here, I'm showing an analyst-based monitoring system that's being run by the Italian government. And so from this, they located about 80,000 earthquakes over this 1-year period to characterize this sequence. Whereas we have used a FaceNet, which is a neural network-based picker, and we managed to detect and locate about 900,000 events over the same time period. So this is an order of magnitude more events. And you can see very clearly when combined with this method of high resolution location of events relative to each other, and so the strength of this increases as we have more earthquakes, you start seeing all these fault structures that was not visible from a more typical monitoring network. And so this is very exciting because we are now being able to use this to very, very quickly characterize seismic sequences, as well as to quantify and characterize the different fault structures and understand the different triggering processes that might be occurring. And when you do statistical analysis as well, having 10 times more events allows you to get more robust results. And so this is the advantage of discovering signals that we already know, right? So we know earthquakes, we know how they look at. So using labeled data, similar to how Google allows us have built a system that can tell us that we are looking at a photo of a cat. This is a similar idea where we are able to look at a seismogram, say that it is an earthquake, and pick the arrival time, and feed it into a system that locates earthquake very, very quickly. But then now moving forward, the question is, can machines do better than humans, right? Because right now, the labeled data are all from manually labeled data, right? And so we are training this, the models to pick as good as the manual labels, right? And so we have looked at the Northern California network. So the blue lines here are the manual picks. So these are test data. And the red lines here are the machine learning picker. So we are comparing, we're using cross-correlation derived arrival times for repeating earthquakes. So we are looking at earthquakes that has very, very similar waveforms. And we are trying to compare and see whether humans are doing better or the machines are doing better. When we compare, we can see that, so this is the differences compared to cross-correlation measurements, which are very precise, because especially for events that are very similar to each other. And we can see that right now, at least this machine learning picker is doing a very similar job. It's comparable to the performance of manual pick. And so we think that this is very encouraging. But then, so we are trying to come out with other methods to judge how good a pick is. that is not based on manual pick, because then we might be able to push the limit and maybe like train models that can do even better than manual pick, and that can improve our earthquake locations and maybe knock down our detection limit as well. So this is what we've been looking at. And then the other thing that we've looked at is that we are trying to see if machine learning can allow us to discover new signals, right? So in this paper that was published in 2017, they use lab measurements where they create earthquakes. So this is a buildup of stress, and then the drop in stress is because an earthquake has happened, right? So they're creating lab earthquakes, and from this they know when an earthquake is going to happen, right? And the time from failure. And at the bottom here, right here, the third panel here shows you can pretty much see it as a seismometer. So you can see an earthquake occurred here, an earthquake occurred here, an earthquake occurred here, and an earthquake occurred here. There are 4 earthquakes. But before an earthquake, we don't, like by eye, we don't really see any special changes in the seismogram. It seems like it's all noise. So when they feed it into a machine learning model, the seismogram, and ask it to predict the time to failure, so this is what they get. So the red line here is the test data, and you can see that they managed to predict the time to failure pretty well. And what ended up happening is that when they then went in, they found that there's actually a lot of background tremor that's occurring, and the amplitude of the tremor is actually slowly increasing leading up to failure. So this is a very exciting result, because this tremor wasn't, this precursory tremors that can actually tell us about the exact stress state of the fault wasn't detectable before, because human eye couldn't identify it. And similarly, we have applied a similar concept to try to see if we can find any precursory signals and forecast geyser eruptions. So geyser eruptions are this. So these are CO2 geysers that erupts water every few days or every couple of weeks. And so we've applied a similar method, and we have found that we are able to classify whether a waveform reflects an eruption or whether it erupts at a time, a duration shortly before the eruption, or it's just background noise. So this is very promising in that it allows us to discover new tremor signals, and hopefully this will improve our understanding of different physical processes that occur before earthquakes or volcanic eruptions or geyser eruptions. And so finally, I'm going to conclude by having a short advertisement. I just want to point out that, so I just joined the Chinese University of Hong Kong, and we have a department of 6 professors. 3 of us focus on atmospheric science research, and the other 3 are focused on geophysics research. And all of us, as far as I know, are actively recruiting students for the next coming cycle, and we have fully funded master's and PhD programs with monthly stipend. You can find more info here, and this is the list of the research topics that we are all working on, ranging from volcanoes to glaciers and earthquake and marine geophysics, as well as atmospheric chemistry and physics and climate dynamics and climate change. So with that, I'm going to end my talk, and I'm happy to take any further questions that anyone might have.
Well, great. Thank you, Yanjoe. And okay, do you take postdocs or do you take visiting scholars?
We do take visiting scholars, and we have had quite a few, and many. I think, yeah, each of the professors have taken visiting scholars. And for postdocs, right now we don't have any active ads yet, but from what I know, some professors do have postdoc money available, and so if we see a good fit, we do recruit postdocs.
Okay, great. Okay, now we are for the audience. Please ask questions. So before you raise a question, please let us know your name and your institution. And when we ask the questions at the very last question, we'll leave for Wei Wang again from University of Southern California, because he did have some previous statement that he didn't finish because they couldn't part of the Yanjoe's talk. Go ahead. Or you could type your questions, then we could read it and Yanjoe could answer them. It's okay if you ask a question in Mandarin or even Cantonese. I think it's okay, because Yanjoe could speak Cantonese and Malay, I think.
Hi, Professor. I am Binghao Wang, and I have another question for the second part of the talk.
Yeah, go ahead.
Can you explain why increasing roughness or heterogeneous can induce a higher p-value?
Right. Okay, so a very intuitive way is like you can think of a fault as having different roughness, right? And each earthquake, so the bigger earthquake are events that occur on bigger faults, and smaller earthquakes are events occurring on smaller faults, right? So a p-value essentially just tells us the relative proportion of larger to smaller events, right? So for a p-value of 1, for instance, for every magnitude 4 earthquakes, you have 10 magnitude 3 earthquakes and 100 magnitude 2 earthquakes, right? So it increases by 10 every magnitude that you step down. So when you have the idea for having more heterogeneity and more rough faults is that you are having smaller asperities. So you can think of that as smaller contact surfaces for small events to happen, right? So when you have more of these smaller events, then the natural translation is that you then tend to have more smaller earthquakes compared to larger ones. So that increases the slope. So what that happens is that the p-value increases. So what that means is that maybe for every 10 magnitude 4 earthquakes, you actually have 150 magnitude 3 earthquakes instead of just 100 magnitude 3 earthquakes.
Oh, thank you.
Hi, Yanjoe. This is Yan again.
Yep.
If no one is going to ask, I'm going to ask one. So my first question is, since you find the p-value varies with the tidal stress induced the Coulomb stress, right?
Mm-hmm.
So we know the Coulomb stress changes happen frequently. So in such short time interval, do you have enough earthquake to get that p-value, or do you use some other strategy?
Yeah, so I'm stacking
Mm-hmm.
events, right? So like when you split, you can see that I split it into 2 kilopascal bins. So at the minimum, right? So I'm looking at intervals between -10 and 15 kPa. So each bin has at least more than 500 events for each bin, and then I do a bootstrap to look at it. But another thing that I did is also I only split it into 2 equal size groups, right? I split the Coulomb into half based on the lower versus higher tidal stress group. So each group has 10,000 earthquakes. Okay? So the red line is made out of 10,000 events, and the blue line is made out of 10,000 events. And you can see that they separate out quite well. So I think we have more events than pretty much any other p-value studies I've ever seen.
Yeah, maybe in the future with the machine learning, you can detect more earthquake to have like a time variation of the p-value.
Yes.
So my second question is just if you see any like general time variation of p-value within time.
So after the eruption, we don't have that many events. So I wouldn't be very confident about it. But either that or we have to use like huge time windows, right? But before the eruption, I think I was aware of another student at the North Carolina University. They have been looking at p-value variations. And I think they see some changes, but the result hasn't been published. Okay. But it's definitely something that we can look into.
Yeah, since some other possibility is if you have accumulated damage, you may change the property of the fault. And that can be also another factor to change the p-value.
Yes.
That's very interesting. Thank you.
Okay, thanks, Yan Zhang from Carnegie Institution of Science, as well as Wang Pinghao from Beijing University. So go ahead, please ask questions.
Should we let, if no one else has questions, should we let Wei Wang finish his previous question that was cut out?
Yeah, please, Wei Wang from University of Southern California.
Hello, yeah, I'm Wei Wang, yeah. Yeah, for sure. I just want to just update the new results. So we agree, like agree with your conclusions that tidal triggering is almost happening everywhere, but it's sometimes especially in the continental scale, it's really hard to detect because the solid Earth tide is almost 1 order smaller than the ocean loading.
Yes.
So, yeah. So basically, like there is a very timely and a novel the Koch template matching catalog.
Yes.
So based on that catalog, we can find some tidal triggering in Southern California because it provides us, very small completeness magnitude earthquakes that's just make it real. Also the second thing is I think we believe like the tidal triggering can easily happen in some specific places. In our study, we used the geothermal field, but for sure, like there could be other places. But basically, based on the catalog, we only find that results. But it's opposite to your conclusion. We find it at the high tide, not the low tide, because we don't have the the magma chamber, and also for geothermal field, there are a lot of normal fault and also stratigraphic fault, which is sensitive to the dilatational strain or dilatational stress. So that is our conclusion. Yeah, similar to our result.
Right. Yeah. I don't think like, so after our study, we also like did a calculation, like if we plug in a different A value, this lower A value that we found into the modeling, and we calculated and we estimated like on continental, like John Vidali had a paper, right, where they had 20,000 events, and we calculated that even with this lower A value, he would not have detected tidal triggering signal with the catalog size that he had. Like he would need a much larger earthquake catalog to get a statistical significant change. So our result is not inconsistent with what they found so far. And the other thing I wanted to point out is that when I say low tide, like, so in the literature people talk about high tide, low tide, but like oftentimes it's confusing what that actually means. So like in Axial, we talk about low tide as it just means low ocean height, right? But in the end, the earthquakes still should occur when there's increase in Coulomb stress change. So sometimes when people say high tide, it just means an increase in stress that for that specific fault orientation, and we see the same thing.
Yep. Thank you.
Yeah, thanks. Thanks for the update.
Hi, Yanjoe. This is Sean from Michigan State.
Hey, how are you?
Good. Long time no see.
Yeah.
I'm terribly sorry that I misremembered the time, so I came 1 hour later and only catch up the last part of the talk. So maybe my question has already been answered. But so I was following your papers recently, and then curious about these B values because for another group of community that's studying intermediate depth earthquakes, we always try to relate B values to fluids or pressures. And of course, for middle ring, there's also some fluids getting involved. So I wonder, so right now it looks like your conclusion is that doesn't really touch fluid, I don't know, poor system or poor fluids migrating. Do you think that's something also important?
Yeah. So yes. So a lot of times when people talk about fluids, they are talking about absolute B value, right? And so at Axial, the B value is high compared to other typical regions, right? So we're talking about B value of what's like higher than 1, right? So the background B value is right. It's somewhere is above 1.1, right?
Yeah,
regardless of where it is. So this could reflect stress heterogeneities or so essentially a background state or the existence of hydrothermal fluids or differences in pore pressure and stuff. But because we are looking at variations wave time, so it's on the order of 12 hours. So we don't think that this effects would come into play that strong.
I mean, can tide change the fluids and then turns out changing B?
Okay, so if it does change the pore pressure, right? That still in the end is a change of the stress on the fall, right? Because then the effective normal stress has changed.
Okay.
Right. I see. But from the previous talk where that you probably missed, where we look at tidal triggering on earthquakes, right? We don't see any time delay between when the earthquake peak and when the tide is. So we were wondering, we was trying to see if we see any poroelastic effects from tidal triggering, and so far, well, at least from what we have so far, we don't see any evidence of that. Which is why we also conclude we didn't think that the B value variation has to do with the fluids.
Okay, thanks.
This is Linghao Wang, and I have another question.
Yeah, go ahead.
So the observation about tidal triggering, is there high tides corresponds to high earthquake rates, and the low tide corresponds to high earthquake rate? Both types exist.
Right. So in this case, when I talk low tide, high tide, I'm talking about different ocean height. And so in this mechanism, as it turns out, low tide should encourage reverse faulting. But then because of normal faulting and the existence of magma reservoir, we see something that's flipped. But during the eruption, the focal mechanism changed, right? So we have normal faulting events, but then during the 1 month of eruption, we are having reverse faulting events. So during this time, earthquakes were occurring preferentially during high tide.
Oh. And on the specific region and time period.
Yeah, so this is similarly at axial, but during the eruption time period.
Oh, okay. Thank you very much.
Hey, this is Naidan Yun from Peking University. Can you hear me?
Yes.
Yeah. I have a question about the final information about the machine learning to detect gather eruption. So, do you mean the machine learning can detect the class one stage and the class 2 stage and the class 3 stage? So I want to know, is there any significant differences between the class 1 and class 2 from the signals, so that we can say they are different?
Right. So just briefly explaining how we train a model. So this is a seismogram, right? So we are recording continuously the signal, but we had a camera right beside the geyser. So we know exactly when the geyser erupts. So that gives us a timestamp. So it gives us something like this, right? Where we know that the eruption happens and we know how far away at each point in time we are from the eruption. But in this case, we split it into different classes, right? So class 1 is quote unquote noise. And then class 2 is precursor in the sense that it's not the eruption yet, but it seems to contain certain information that allows the machine to tell us that an eruption is coming up soon. And so how we infer this is that there is presumably some tremor that's ongoing, or some change in the seismic waveforms that's being recorded by the seismometers that gives this information that we are close to eruption, and that differentiates it from, say, the signals that is like 5 days before an eruption. Does that make sense?
Okay, so thank you.
Okay, thank you very much. I think that's the end of our seminar today. And on Sunday, we have Huang Fang from Australia giving us talk about the machine learning applied in serpentization process, the geochemistry talk. And next Thursday, we will have D. Kim from University of Maryland giving a talk about applying the machine unsupervised learning method of using sequencer to study the Earth's core mantle boundary. Okay, thank you very much. And thank you again, Yanjoe, for your talk.
Yep, thank you all for being here. Bye-bye.
Bye-bye.